next speaker is Lawton from George Mason University, and his title is Flawed Groups. Yes.
All right, very good. Yeah, to the organizers and Professor Choi, I want to say 감사합니다, and I want to ask that the participants feel comfortable asking questions, and ask maybe at least Hana, but maybe dual, perhaps set, but definitely not net questions, because net would be too much. But that's about the extent of my Korean. So I'm just going to go ahead and stop thanking people now and get started with the talk. So so I'm going to tell you about flawed groups. So this is a class of groups defined by looking at the topology of the moduli spaces of the group. But anyway, I'll say more about that when we get to it. But so here's the outline. So I'm first going to tell you about character varieties, and this is a slightly different point of view of what Segol told us. But it's consistent with what Segol said. And then I'll give you some very simple examples of character varieties that use only linear algebra. I think we're getting some feedback here. Hopefully somebody can mute if they need to. And then I'm going to define what flawed groups are, and then tell you some past results related to them and some new results. And then I'll end with conjectures and questions. Okay, so to make a character variety, I think of it as needing two types of ingredients. Okay, one of them I think of as a topological ingredient, and and the avatar of that topological ingredient is a finally presented group. It's thought of as a discrete group, so the discrete topology. I think of it. Well, anyway, before I say why I think of it as a topological piece of data, let me just make sure everyone's on the same page. So finally presentable groups, what does that mean? That means that the group admits a presentation where there are R letters. Okay, I'm enumerating them gamma 1 through gamma R, and then there's a finite collection of relations. Okay, so the relations are words in the letters gamma I plus or minus 1. Okay, and it's in our understanding, is that in the group, whenever you see that string of letters corresponding to Ri, then it trivializes. Okay, it just becomes 1. Okay, so examples, we have free groups. Okay, this is the case where there are no relations. Okay, we also have free abelian groups. So this is the case where you have the only relations you have are commutator relations. So for every pair of letters gamma I and gamma j, you have gamma I times gamma j times gamma I inverse times gamma j inverse are your relations. Okay, so it just says that the letters commute. Okay. More generally, the fundamental group of any compact manifold or orbifold is a finally presentable group. And that's sort of why I think of it as a piece of topological data. I mean, more generally, for every finally presented group, there is some CW complex whose fundamental group will realize that it might not be a manifold, but anyway, so that's how I think of it. Okay, so the second ingredient to make a character variety is I think of it as a geometric ingredient. Okay, it's also a group, and that ingredient are Lie groups that not just any Lie group. I guess in principle you could just start with any Lie group, but I want to restrict the class of Lie groups that I'm concerned with, and I want to restrict it to a class that is morally like compact Lie groups. So indeed we'll start with a compact Lie group, and there's a general theorem. It's not in the definition, but it is a theorem that every compact Lie group is a real algebraic group. So what does that mean? That means that it is the simultaneous zero set of a collection of real polynomials. So polynomials with real coefficients. Okay, and you're asking for the solutions, over R. Okay, so the simplest example is U1. Okay, the unitary 1 by 1 matrices in the unitary unitary 1x1 matrices. Okay, and that's the circle. And I think Segal mentioned that in her talk. X squared plus y squared minus 1 is a variety, and you look at the solutions over R, and you get a circle, right? Okay. So we're going to define GC here to be the complex zeros of the polynomials that defined our compact group. Okay, so going with the analogy, if we were looking at U1 and you asked for the complex zeros of U1, then you get GL1. Okay, you get GL1 if you did that. And that's basically because if you can do a change of coordinates, right? So, let U be X plus IY and V be X minus IY, then the equation X squared plus Y squared minus 1 factors as U times V minus 1. Okay, and that's exactly the defining relation for GLC when you look at complex solutions. Okay. All right, so any and every affine algebraic group over C that arises in this fashion is called reductive. Now, what does that mean? Well, we could just say, look at the complex zeros of compact groups and say those are our reductive groups. But the traditional definition of a reductive Lie group is one that is when either the unipotent radical is trivial or the radical is an algebraic torus. And if you use that more traditional definition of a reductive group, then you can prove, and it's a non-trivial theorem, that group is the complex zeros of a compact group. Okay, so the definition I'm giving you is consistent over the complex numbers with every other definition of reductive group. All right. But that's still a little bit too small. I want a bigger class of groups. So I want to now say, well, okay, we have these complex reductive groups. Now we want to look at the real points of them. Okay. And then I want to say a group is real reductive if it's real reductive if it's situated between the identity component of the R locus and the R locus of our complex reductive group. Now, at this point, it's very natural for people at a first reading of this definition to say, well, doesn't that just get me back where I started? I started off with a compact Lie group, and it was a real algebraic group. I complexify it, and now I'm realifying it back. Don't I get back to where I started? Well, let's go back to that simple example we just had with U1, and then complexifying it to GL1. Well, another equivalent way to describe GL1 is the determinant is non-zero, and if I did that and I said, what are the R points, right? Then I get GL1R instead of U1. So in other words, a complex reductive group admits different real models. Okay. And so different real models, when you look at the R locus, you get different groups. So more generally, if I start off with, say, the unitary group, I complexify, I get GLN, and then I can also, I can look at the R locus with a different real model of GLN, and I get GLR, okay, instead of, back to UN where I started. So I want to allow those different models in this definition, okay? And so, start with a compact group, complexify, forget the polynomials I started with, just think of that now complex reductive group. And then I'm going to say, for any real model, look at the R locus, and anything that's situated between that R locus and the identity component of that R locus, that's Zariski dense, excuse me, I need that condition too, is going to be called a real reductive group. Okay, that's the general class I'm going to be dealing with. And if all of that was crazy, you didn't understand anything I just said, then just think of SLN or C or R or any of these groups down here. Okay, these are all examples of real reductive groups. And you'll be fine if you think of it, your favorite examples in what I'm about to say. Your favorite classes of examples. Okay. Okay. So that's so those are the two ingredients: a topological ingredient, a discrete group, finally presentable, and then a geometric ingredient, a Lie group in this class of real reductive groups. So let me stop here and ask: are there any questions about either of those two things? Because we're building up the definition of a character variety, and those are the two ingredients. So are there any questions about either of those two ingredients? No, people are cool. Okay, so discrete group, Lie group. All right, real reductive Lie group. All right. Okay, so the theme, the reason character varieties are important in mathematics is because they're philosophically they take these two ingredients, a topological ingredient and a geometric ingredient, and you're asking about the relationship between these two ingredients, right? And so you have two groups, and so you want to look at a group homomorphism. Okay, so there's, anytime you have geometry, you always have topology, right? So the interesting question is, if you have something topological, what are the different ways to impose geometry on it, if any, right? And so that's kind of, loosely speaking, why we're looking at homomorphisms from gamma to G. Okay, because we're looking at different ways to impose geometry onto topology. Okay, so two natural incarnations of this is on the one hand, you can think of say principal G bundles over a space whose fundamental group is gamma. This is one avatar of this philosophy, and then the holonomy homomorphism gives you a bijection between those bundles and these homomorphisms. Okay. Another way you could also, if you wanted to, you think in the class of Lie groups we're dealing with, G, that's linear reductive, all of them emit a faithful representation into GLV for some vector space V. Okay. And so you can think of this in terms of representations. And in here, we're looking at the sort of geometric representations of gamma. Okay. And just keep that in mind. Okay, so but at this point we just have a set of homomorphisms from our topological ingredient to our geometric ingredient, and we want to do more than that. So we want to give it a topology, topologize the set. So since gamma was generated by R things, there's a natural evaluation map which takes the generators of gamma into the Cartesian product of G with itself R times. Okay, and this map is always injective. It's generally not surjective, but it's always injective. So this identifies the set of homomorphisms with a subset of G to the R. Okay, and G to the R, since G was a Lie group, this is a manifold. Okay, so we have a subset of this manifold, and so we have a subspace. So this gives a natural topology on the set of homomorphisms, and this topology is independent of the presentation of gamma. And why is that? Well, if I had another presentation of gamma, that would give me an automorphism of gamma, and then that would induce a homeomorphism on the set of homomorphisms. Okay, and so up to homeomorphism, this topology on the set of homomorphisms is independent of the presentation, even though we're using a specific presentation, you're right, to define the topology. Now, there is another way to do this internally. That's equivalent. We can look at the compact open topology where we gave, like I said, gamma the discrete topology, and since G is a Lie group, right? There's a topology here, but I like this sort of external definition a little better. It's a little bit easier to see what this topology is. Okay, so we've topologized the set of homomorphisms. Okay, but we don't, right? But we actually want to look at this set up to some natural equivalence. Okay, and so in the case where I said you could think of this as representations, the natural equivalence classes in representation theory is that of conjugation classes, because they're intertwiner maps with respect to the action defining the representation. In the case of bundles, where we identify the set of homomorphisms with respect to holonomies of say principal bundles, then that identification required a choice of a base point in your base space, but that's not really a natural choice, right? So it's not really important in the with respect to the bundle, right? And so if we change the base point, that induces conjugation on the holonomy. Okay, either way, either point of view, and lots of other points of view too, a very natural equivalence relation to put on this set, if we're thinking of this as encoding the ways to impose geometry onto topology, is that of conjugation. Okay, so to really understand this sort of this space, okay, we would like to look at the quotient space by conjugation. However, whenever you want to understand something, right, you would like to be working with a space that you can analyze, right? I mean, and unfortunately, if we just quotient by conjugation, this space, this set of homomorphisms quotient by conjugation is very bad. It's not even T1, okay? It's very, it's very ugly topology. And so we want to approximate it. We want to approximate the thing we want to care about by something that's at least it's amenable to analysis. Okay, and so the least we can do is throw out the bad points, throw out the points that make this thing not T1, in particular the points that are not closed. Okay, now I'm working in an analytic topology. I know if we're thinking of this algebraically, I understand there's this Zariski topology, which is not Hausdorff and all kinds of other things, but that's a different story, a different point of view. I'm really thinking of this in a setting where I have small open sets, and if I have small open sets and that's the kind of topology I'm dealing with, then I really want it to be at least T1, hopefully Hausdorff. So what I'm going to do is I'm going to throw away the points that would be points in the quotient, right? The orbits, the conjugation orbits that aren't closed. Okay, so I'm going to throw those points away. I'm going to just take the subspace of the homomorphisms that consists of points that have closed orbits. And closed makes sense because I put a topology on it on the previous slide. Okay, these are called polystable points. The word comes from either GIT or also from the theory of bundles. There's stable and semi-stable and polystable and other things like this. But here we just mean the points that don't have closed orbits. That do have closed orbits, right? The polystable points are the ones that do have closed orbits. We're throwing away the ones that don't. Okay. So then I have the G character variety now, finally. So it's the space, the conjugation orbit space of this set of polystable homomorphisms. Okay. And this is probably a little different than Segal defined, but it's consistent within the setting she was working in. Okay. So let me say a few things. First, as I mentioned earlier, just throwing away these non-closed orbits takes something that's not T1 and makes it T1. Okay, that's good, a T1 topology. But it turns out, because we're dealing with Lie groups that are real reductive, there's a general theorem of Richardson and Lectuee from 1990 that actually says that this space actually is Hausdorff. We get up to T2 for this. Now, this isn't just from the construction. This is because of the restricted class of Lie groups we're working with. Okay. But anyway, in this class, this quotient actually is Hausdorff. And not only that, one way to prove this is to show that this thing naturally embeds in some affine space. And in that embedding, it's closed in the sense that every space is closed in itself. So it's not really informative here, right? If you just look at it as the definition, right? But it's closed in some affine space. So it may be better to say it's complete. And in particular, that implies it's Hausdorff. Okay. And we can say more if G happened to be real algebraic, and that's not necessarily true, right? So in my class of real reductive groups, the identity component of GLNR is there, and that's not real algebraic, it's semi-algebraic, right? Because it has an inequality necessary to define that component, right? The determinant is greater than 0, right? Okay. And so, but if G was real algebraic, then we can actually say the character variety is semi-algebraic, which is a very nice structure to have, because in particular, every semi-algebraic space emits a CW structure. So we want to understand the topology of these moduli spaces up here. Then the fact that if we're dealing with the case where it's semi-algebraic, we're in good situation. And in particular, right, both the complex reductive and the compact cases are cases of Lie groups that are real algebraic. Okay, if G was compact, every orbit's closed, so we don't throw any points away. So that's one case where the character varieties, we don't even need the star, right? It's just the honest quotient space. And in that case, we don't have any of these weird, Hausdorff, non-Hausdorff problems. And of course, that's, in that case, it's a semi-algebraic space, right? Every semi-algebraic space is Hausdorff in the analytic topology. not the Zariski topology. Okay. All right. And then the last case, and this is the case I think that Segal was talking about, when G is complex reductive, then the character variety is identified in the analytic topology with the geometric invariant theory quotient. Okay, which is if we're just talking about the C points, this is the max spectrum of the ring of invariance. So you look at the coordinate ring of the homomorphisms, you look at the ring of conjugation invariance, subring of conjugation invariance in that coordinate ring, and then you look at the max spectrum, and then you get the GIT quotient. We're in the affine variety setting, so that's all there is to it in that case. If we were in a quasi-projective setting, we'd have to talk about ample line bundles and things, but we're not. Okay. And in good situations, like Segal was talking about, this natural algebraic structure from GIT theory that can be imposed on the character variety has an integral model, or maybe an integral model where you possibly invert some finite number of primes, and consequently you could ask about finite field points or R points for any ring if it's where the characteristic isn't of the ring is not any of the primes you had to invert. Okay. All right. So that's the definition I'm working with for the character variety. Now, before I go on to do some examples that just require linear algebra, are there any questions at this point?
Can I ask a question though?
Yeah.
It's probably the basic definition thing, but in the definition of a G character variety of gamma.
Yes.
So we already consider the set of all the closed orbits in the above.
Yes.
But if we consider the action, then isn't it just the Helm set, the original Helm set? So
no, it's not. I mean, it's definitely not the original Helm set, unless, I mean, if in general, usually you will have non-closed orbits. So if G was compact, then every orbit's closed, so you don't throw any points out. But if G is not compact, you're generally going to have non-closed orbits. Yeah, so you generally do throw some things out. Now in with respect to geometric invariant theory, the way Segal defined it is consistent in the following, because of the following fact: if G is complex reductive, every the closure of any orbit has a unique, and this is the key point, unique subclosed or closed suborbit. Sorry, I had my adjectives backwards. Closed suborbit. So you take any orbit, you look at the closure, there's a unique suborbit in that closure that's closed naturally. So in the way Segal defined it, and in GIT theory, you define sort of an additional equivalence relation on the set of orbits, where you say two orbits are equivalent if and only if their closures intersect. But because every orbit closure has a unique closed suborbit, throwing away all the there's a bijection between the polystable quotient, which is what this star thing is called, and the GIT quotient. And then it's a theorem of Luna that in the analytic topology, that bijection is in fact a homeomorphism in the analytic topology. But I don't know if I answered your question or not. But one of the examples I'm about to give will illustrate a case where there's a non-closed orbit. So you'll see it in a second. But
I guess
did that answer your question or no?
I just want to make sure that if the home star is just when you construct a home star, you first consider the orbit and then take the closures of it. No,
you don't. No. Helm star is a subset of all of Helm. So think of it like, you're not taking the closure of the orbits. What you're doing is you're looking at the orbits one at a time, and you're asking the question, a Boolean question: is the orbit closed or not?
I see.
So closed is does it equal its own closure, right?
I see. Then
and if the answer is yes, you keep it, and if the answer is no, you remove it, and you do not include it in that set.
I see. I see now.
Does that make sense?
Yeah, that answers my question. Yeah.
Okay. All right. Good. Any other questions? Okay. All right. So the simplest examples we could deal with is just of the discrete group is just the fundamental group of a circle. Okay, well, the simplest example is a trivial group, but then the moduli space is a point, and that's not very interesting. So let's do something a little bit more exotic than that. So the simplest case is just the integers. Okay, just that's it's a free group of rank 1. Okay, all right, and then the simplest non-abelian case is SL2C. Okay, of course, we could do an abelian case, but then the conjugation action is trivial, and then we've trivialized, and then we just get back to Hom space again, back to the beginning, and it's not very illustrative of what happens. So we want a non-abelian Lie group. Okay, but SL2C is pretty simple among that class. Okay, of non-abelian Lie groups, a complex reductive to start with. Okay, so those are the 2 ingredients. That's our topological ingredient and our geometric ingredient. Okay, and then so now the evaluation map creates a bijection from the homomorphisms from Z to SL2C to just SL2C, because this is a case where there's no relations and the evaluation map is in fact bijective. So we just get SL2C back. Okay, so said differently, every homomorphism is completely determined by where you send the generator, gamma. Okay, and so you can identify homomorphisms with just the group itself. Okay, and that's the topology we're dealing with. Okay, so for every homomorphism identified with a single matrix, right, we're going to use rational canonical form where we can to, because remember, we're looking up the conjugation, right? So we're going to just define this matrix epsilon sub t to be essentially the rational canonical form of a 2x2 determinant 1 matrix. Okay, so you can check here that this matrix has determinant positive 1, right? So it's 0, minus 1, so it's determinant 1. Did I say minus 1? I meant 1. So determinant 1, okay? And it has trace t, okay? And the characteristic polynomial is completely determined by the trace, okay? All right, and so for any homomorphism, right? So that the trace, and the trace makes sense because it's identified with a matrix. So the trace is not plus or minus 2. So then it has exactly 2 distinct eigenvalues determined by the trace. So you can write down the characteristic polynomial, and you can write the quadratic formula down, and you'll see under the radical, it's like t squared minus 4. And if you, and t squared minus, you have 2 distinct roots as long as t squared minus 4 is not 0. So that's equivalent to t not being plus or minus 2. Okay? All right, so what that says is for every homomorphism, there is a matrix, depending on the trace, that conjugates rho to this epsilon t as long as t is not plus or minus 2. Okay, all right. And in that case, there's only one conjugation orbit corresponding to that trace. Okay, and so consequently, those orbits had to be closed. Because if it wasn't closed, then there would be another orbit intersecting that orbit, and they would have the same trace. But there's only one. The trace determines for every trace, right? There's, if there's distinct eigenvalues, there's only one orbit that corresponds to that trace. So these all correspond to closed orbits. Okay, now what's the problem traces, right? Well, when trace is plus or minus 2. So in that case, rho is either conjugate to epsilon plus or minus 2 or plus or minus the identity. Okay, because those are the only matrices that have, right, up to conjugation that have trace plus or minus 2. Okay, so in the former case, it's, if the trace is plus or minus 2, but it's not the identity, then it's upper triangulizable, and it looks like this. Okay, and in that case, if we conjugate this matrix by this diagonal matrix, we get this. And so this gives us a sequence in the orbit because we conjugated this matrix by something, and so it's in that orbit, right? And so letting n go to infinity, we see that the limit is the plus or minus the identity. So that tells you that orbit's not closed, right? Because it has a limit point, not conjugate to it, right? Epsilon plus or minus 2 is not conjugate to plus or minus the identity, right? They have different, say, eigenspaces or something. There's lots of ways to distinguish them, using, basic linear algebra. Okay, so what do? We throw away the non-closed orbits. So we throw away the orbits corresponding to epsilon plus or minus 2. And what we had is when epsilon wasn't plus or minus 2, for every complex number t, we had a closed orbit. So the space of closed orbits up to conjugation was before we before we considered plus or minus 2 was the twice punctured complex plane, right? Just C minus plus or minus 2. Take away those two numbers, okay? But then we put them, but then we had one for each of for 2 and minus 2, you had 2 orbits. We threw away 1 for each, and so we plugged the hole with the points, and so consequently, the moduli space is just the complex numbers. Okay, just parameterized by the trace. And you can also see if we didn't throw those away, then we'd have 2 double points at plus or minus 2, and we'd see it's not T1, right? We wouldn't be able to separate those double points. Okay, and definitely not Hausdorff, but not even T1. Okay, but we did throw them away, so this is the example in this case. It's just the complex numbers. Are there any questions about this example? I think it illustrates what happens with open orbits, and I'm sorry, not open. They're not open, but they're open in themselves. But anyway, sorry. I mean, the non-closed orbits. Throwing them away, what you get, how it gives you a Hausdorff space, and you also can see if you want to think about what Segal had said. To tie it to geometric invariant theory, right? If you want to use GIT theory, then what's the ring of invariance? Well, the ring of invariance is actually generated by the trace itself. Okay, and so the spec of just T is just C, max spec. Okay, there's a number of ways to see that. I mean, the up to conjugation, is a risky open set is the diagonalizable ones, and then all the only thing you can choose to do is act by the Weil group, which is the symmetric group on 2 elements. And if you look at you look at the theory of symmetric polynomials, you'll see that it's generated just by the sum, in degree 1, which is the sum of the 2 eigenvalues. Okay, which is the trace. Okay, all right. Anyway, right. Okay. So let's keep with just one matrix, but let's change the Lie group. So now let's look at SU2, but the same discrete group gamma, just integers, right? But now in this case, we see that how do you parameterize SU2? Well, it's a 2x2 matrix where the top row is sine and cosine, cosine and sine, and then the second row is minus sine and then cosine again. Okay, but it's still parameterized by the trace, just like before. So now we don't throw any points away because every orbit's closed. But the trace still determines each orbit. Okay, and so, but now what is the trace of that matrix? Well, the diagonal was cosine, so the trace is 2 cosine. And so now let cosine vary from 0 to 2 pi, and you get minus 2 to 2. You see, and so that's another example, right? But the nice thing about this example is it shows that these spaces, even though they're called character varieties, are not always varieties. Because minus 2 to 2 is not a variety; it's a semi-algebraic set. Okay, so the character variety is sometimes not a variety in the generality that I've defined it. Okay, if we're dealing with a complex reductive group, it's always going to correspond to a variety because it's by GIT theory. But if we're allowing other Lie groups, then we get things that are not always varieties. Okay, so but that's the compact case. But let's look at a Lie group that's real reductive but not compact and not complex reductive. Okay, but still stay with the integers. So let's look at SL2R. Okay, this one's more fun. Okay, so we get to see a lot more of what happens. And again, this is the simplest case, right? But it's just 2x2 matrices and one, in a free group of rank 1, right? It's a fundamental group of a circle. That's how I like to think about it. All right, so as with the first example, the closed orbits correspond to diagonalizable matrices over C. But now remember, we're working with real matrices. So diagonalizable over C it doesn't mean diagonalizable over R. Okay, so if it happened to be diagonalizable over R, then the diagonal form would look like this: a 2x2 matrix with, is determinant 1, so there'd be lambda and its inverse on the diagonal. And since we can permute, by the I guess what is the matrix 0, 1, minus 1, 0, perhaps I don't remember exactly what it is, but it's like the Weil group permutes the things, and so we can conjugate this to these two guys to each other. And so remember, we're looking at conjugation equivalence classes, right? And we're conjugating that conjugation can occur in SL2R. So we're not working outside of the group. That's the key thing here, right? We're conjugating by this group, okay? But anyway, because we can switch the order here without loss of generality, we can assume the absolute value of lambda is bigger than its inverse, okay? And because of that, we can say that the elements in this moduli space corresponding to the diagonalizable elements over R is exactly this set here. And we can just assume lambda is not right between -1 and 1 because we could chose the ordering. Right? Because if lambda is bigger than 1, 1 over lambda is less than 1. And because I can always choose the top left entry to be bigger because of the have absolute value bigger, because I can permute, right? Then I get a 1-to-1 correspondence with this set. Okay? All right. So now we have to consider, what about the diagonalizable matrices that are diagonalizable over C but not diagonalizable over R? Okay, well, this set looks like this, right? But now the eigenvalues are complex numbers, but because we started off over, and this diagonalization occurred over C, so not by SL2R, by SL2C. Okay, I'm just showing you what it looks like if you did that. But the matrix originally started off in SL2R though, so that means the trace still has to be real, because it started off real, so it's still real after you conjugate, because trace doesn't, you can conjugate by something complex that was real, it doesn't change the trace, because trace is conjugated variant. So therefore, Z plus 1 over Z is a real number. Now, if you write out what that means, it means the absolute value of Z is 1. So that means these matrices are actually in SO2C. And hence, the ones corresponding to SL2R belong to SO2. Because if you're in SO2C intersect SO2R, then you're in SO2R. And that means you're of this form. Okay. The only conjugate matrices of this type are A theta and A minus theta. So let's go back here, right? So here's A theta, right? Now, if I change theta to minus theta, the cosine stays the same. Right, but what happens on the anti-diagonal? The minus sign switches to the lower left because sine is an odd function. Okay, but if I'm conjugating in SL2R, this is a subtle point here. I can't switch those. I can't get from one of those, the minus sign in the upper right, to the minus sign in the upper left by conjugating in SL2R. Okay, I can do it in SL2C. And I can do it actually in GL2R, but I can't do it in SL2R. Okay, so those different matrices, even though they have the same trace, are not conjugate to each other in SL2R. So what happens is you get this as the moduli space. So you get the two wings corresponding to the matrices that were diagonalizable over R, but then you get this whole circle corresponding to the matrices that were diagonalizable over C but not R. And this actually shows something even more subtle, that the space of the character variety is actually not parameterized by characters. So not only is it not necessarily a variety, it's not even, the word character doesn't even make sense, because the trace, let's go back up to that matrix, right? The trace doesn't see the difference between the anti-diagonal. Right? The trace, if I put the minus in the upper right or the minus in the lower left, the trace gives me the same value. So what I actually need to distinguish the points in the upper hemisphere with the lower hemisphere is a different invariant called the Pfaffian, which is like the square root of the determinant, which is not a polynomial in terms of traces. And if you wanted to study character varieties of even orthogonal groups, even over the complex numbers, you'd have to study Pfaffians because they're actually important in the study of those character varieties. But we see that the necessity of looking past traces already in this simple example. Okay, now why did I make you go through these examples? Well, on the one hand, I wanted to show you that you can see a lot of the general properties of character varieties with some of the simplest cases. But the other one is I wanted to motivate the definition of a flawed group, which I haven't given you yet. So let's make a couple observations about those examples I just gave you. The first one is that C deformation retracts to the interval. Well, they both deformation retract to points. Okay, I understand that. That's not very illuminating. But this interval is a subset of C, and it does deformation retract. Okay, so just keep that in mind. The second one is this one's not as trivial. That the character variety of SO2 is abelian, so it's just the homomorphisms, which is just SO2 back. So it's S1 because SO2 is S1. And that S1 is that big circle we saw here for the SL2R character variety. And so the SO2 character variety lives inside the SL2R character variety, and those wings contract away. And so again, you have a deformation retraction of these moduli spaces. And the next thing to observe is SU2 is maximal compact in SL2C, and SO2 is maximal compact in SL2R. So if you look at the character varieties corresponding to the complex, to the real reductive group and its maximal compact and compare them, we see the moduli spaces are actually homotopic to each other. Okay, so with that in mind, here's our definition. So actually, I should stop. Are there any questions? Let me stop here to ask for questions before I give the definition.
I have a brief question just regarding the first character variety of SL2C.
Yeah.
I remember that in the example, essentially what you did was that you parameterized by the trace, but you have to throw away 2 points corresponding to the trace plus minus 2, right?
Yes, yes, right.
So why is the character variety still C and not C minus those 2 points that we throw away corresponding to plus minus 2?
Yeah, okay, good. I didn't throw away all 4 points. Remember, there's 4 orbits there. There is the for trace 2, there's the identity and then epsilon 2. Mm-hmm. And for trace minus 2, there's minus the identity and epsilon minus 2. Mm-hmm. There's 4 orbits there. I didn't throw away all 4, I just threw away 2 of them. So I had 2 points missing and 4 points to fill them. I took away 2 of the 4 points, and then I filled the 2 missing points with 2 of the orbits.
Oh,
so then
I see. Yeah,
yeah.
Okay, I see.
Okay.
Thank you.
Yeah, sure. Any other questions? Okay. Let's see. All right, so here's our okay. So as I mentioned before, if the group is real algebraic, like for a complex reductive group G and a maximal compact K, then the moduli spaces are real algebraic. And real algebraic, real semi-algebraic. But in semi-algebraic spaces they all emit CW structures. Okay, so this slide, the first thing that I'm saying is there is a natural inclusion of CW complexes. Now, this is not at all obvious. I mean, there's a number of things happening here, right? The K character variety here is quotient by K. The G character variety is quotient by G, right? It's when you map a representation, an equivalence class for the K character variety to the G character variety, you're increasing the equivalence relation, right? Because you're quotienting by a bigger group. So there's no reason a priori to think that this would be a one-to-one map. Okay, but it is. Okay, but that's something to prove. Okay, but morally, it's because the action of a maximal compact determines the orbit. Okay, but anyway, I'm not going to prove that, but I'm just stating this is part of this statement, emphasizing it. The other part is that the CW complexes on each side of this map actually correspond to each other. Okay, but that's a theorem essentially, or a lemma maybe. Okay, all right. So there is a natural inclusion of CW complexes with respect to complex reductive and compact groups defining corresponding character varieties. Okay, gamma is the same in each picture. Okay. So with that statement out of the way, we're going to say that gamma is flawed if this map is a strong deformation retraction for all connected reductive G. And I'll say it's flawless if it's not a strong deformation retraction for any non-abelian G. Okay. Okay. So the philosophy here is that we're defining a property about gamma, and we're defining it through the lens of the moduli space of representations of gamma, geometric ones, and we're quantifying over the different geometries that you can use to, define the geometry on that topology, back to that philosophical statement I started with. Okay, but in the bottom line is you have a property about character varieties, and you're quantifying it over the Lie group used to define the character varieties. And if you quantify over, if you have a persistent property that exists as you quantify over the different choices of G, then this should leave you with some sort of just basic group theoretic property of gamma. Okay, and perhaps it should be considered as a general feature in geometric group theory. Okay, so let's look at some examples of when this holds and when it doesn't. Okay, what time is it, by the way? Okay, it's 9:55, and we started at what, 9:10 or a little after 9:10?
Yeah. So maybe you have maybe you can give 10 minutes or something. That's probably okay.
Yeah, or maybe 15, so we have an hour. Okay. if you're amenable to that. Anyway, okay. So the first theorem is that free groups are flawed and actually real flawed. So I defined flawed only in terms of complex reductive groups, but if you quantify over all the larger class of real reductive groups, then we'll call that real flawed. Okay, so this is a theorem that occurred, over a number of different papers, 2009 and 2015, originally with Carlos Florentino, myself, and then we added a number of other co-authors for the real case. When we learned about Richardson's extension of Kemp-Ness theory to real reductive groups, anyway, and we were able to adapt our original arguments to that larger setting. Loosely speaking, or before I say anything more about that, one naturally wonders if this situation generalizes to arbitrary gamma, and you can find counterexamples from the work of Atiyah and Bott and Hitchin looking at surface groups. Okay, so this property doesn't always hold. It's natural to think it always holds because G always deformation retracts to K. So you might imagine that deformation retraction generally gives you a homotopy equivalence between the corresponding moduli spaces, but it doesn't. Okay, it's that's not the case. But for free groups, it is. And loosely, the proof is like it has three main ingredients: it has Kemp-Ness theory, the general polar decomposition for Lie groups, and Whitehead's theorem. Okay, so since I'm running out of time, I'm just going to do this kind of quickly. But I don't know. Can you guys see my mouse? Do you guys see people?
Yeah, I can see it.
Yes.
Okay, good. Okay, great. So so I'll just say what are the pieces. So in the free group case, the homomorphisms of a free group into G is just a Cartesian product of R copies of G. Since G deformation attracts to K, then that tells you the homomorphisms, the G homomorphisms deformation attract to the K homomorphisms. That's just kind of immediate. That's the polar decomposition bit. Now, what is less known is that actually happens in a K, not G. It's not true for G, but a K conjugate equivariant way. So that tells you that this space is homotopic to this space. There's a deformation retraction between these two things here. Okay. Now, Kemp-Ness theory basically says that you can identify this space here at the bottom with a subset of this. That's what this sigma is. It's kind of a section. Okay, you can identify it with a subset here. And once you do that identification, this space here, deformation retracts to this space as identified as a subspace. So between Kemp-Ness theory and what's known about the general Lie polar decomposition tells you that these two are homotopic. Okay, and these two are homotopic. So by transitivity of homotopy equivalence, these two are homotopic. Now, that's not what the theorem says. The theorem says that there's actually a deformation retraction between these things directly. And just because you have homotopic spaces doesn't mean that there's a deformation retraction. But Whitehead's theorem says that if the homotopy is induced, even a weak homotopy, if it's induced by an inclusion of CW complexes, then a homotopy actually can be upgraded to a strong deformation retraction. And so what you do in this case is you show that the homotopy equivalence that comes from these two and these two separately is actually induced by this inclusion that I mentioned earlier, which is an inclusion of CW complexes in general for any gamma, let alone for free groups. Okay, and then you can employ Whitehead's theorem. Okay, that's loosely what happens, and you can do the whole thing for real reductive too. It's a little bit more complicated, but basically those same moves work. If you analyze it more closely, and you actually define a map here based off Kempf-Nest theory, you can show that you can do that in a way with certain choices, because Kempf-Nest theory requires you to make choices with everything, that you can make the right choices so that this whole global diagram actually commutes. And then you can see that then you can show that going up, over, and down actually defines a strong deformation retraction from this to here directly. But that takes a little bit more analysis. You don't need to actually look that closely if you appeal to Whitehead's theorem. Anyway, that's a sketch of the proof. So what about the next example? Abelian groups. Well, turns out finally generated abelian groups are flawed as well. And we're allowing torsion here too. So not free abelian groups, but any finally generated abelian group is flawed, and also real flawed as well. Okay. And so what are the, let me stop here. Are there any questions at this point that anybody wanted to ask? All right, so how does this proof go? Well, you kind of cheat. That's how this proof goes, okay? So we don't, we don't actually get a similar nice picture as we have here, where we can just find everything explicitly. So let A be our abelian group, our finally generated abelian group. G is our real reductive group. What you do is you look at this weird set here. Now GSS is not a group, so this looks very strange notationally. GSS is the set of semi-simple elements in G. Okay, so think diagonalizable in SLN if you want, but there's a generalization of that notion for arbitrary real reductive. Okay, all right. So and A is finally generated, so it has a finite number of generators. So think in terms of the evaluation map. You can identify every homomorphism with a tuple, a ordered list of elements in G. And so we're going to define this set Hom A GSS to be the tuples which have every component semi-simple. Okay, the tuples that are homomorphisms, and every element in that list is semi-simple. Now that is a G conjugate invariant subset of the homomorphisms, and what you do is you prove that the quotient by G, and they're all polystable points too, by the way. So we're not including anything we would have thrown away. That's also part of this statement. And then you look at the quotient by conjugation, and we show that it actually is homeomorphic to the character variety. That's step one. Now, step two is you do the same game for the compact group, the maximal compact in G. But now you don't look at semi-simple. What you get in the right here is what are called the, I think Costant called these the elliptic elements. These are elliptic elements. So they're the G conjugation translates of things in the maximal compact. Okay, so they're not necessarily points in the maximal compact, but they're conjugates of things in the maximal compact. And you define this set Hom A G of K in the same way as we did Hom A GSS. You look at the homomorphisms of A so that when you write them as a list of elements, okay, with respect to a presentation of A, each element in that list is elliptic. And again, it's a G stable subset base of the homomorphisms, and so we can look at its quotient. And when you do, we prove that it's the K character variety. Okay, now the last step is you show that forget about the quotient, that this space here, the homomorphisms, the semi-simple homomorphisms, G equivariantly, not K equivariantly, G equivariantly deformation retracts onto the elliptic homomorphisms. And how do you do that? Well, basically, every semi-simple element is morally, with respect to some faithful representation, is diagonalizable. And so its diagonal form, it has a bunch of eigenvalues, and those eigenvalues you can write as R e to the I theta. Well, you contract the magnitude of the eigenvalues, and if you contract the magnitude of the eigenvalue up to G conjugation, you end up with a G conjugate of something that is in the maximal compact. That's the main idea. And so you end up here. And then now, since it's G equivariant deformation retraction, that means that the quotients by G deformation retract to each other. And given the isomorphisms in 1 and 2, that proves the theorem. Okay. Are there any questions about that? All right. So this one I'm just going to skip over because I got 5 minutes, I guess. So after some of the work that Florentino and I did, Indranil Biswas and Carlos and Florentino, they looked at the counterexamples we had and they said, well, I wonder if they're always counterexamples. And it turns out they are. So a closed surface groups of genus greater than or equal to 2 are flawless. So they not only are there counterexamples to this deformation retraction property among closed surface groups, in fact, all of them, none of them for any G, in fact, admit a deformation retraction between the 2 moduli spaces. And the way you prove it is basically you use the correspondence to the character variety to the Higgs bundles and the correspondence of the K character variety it corresponds to the Higgs bundles with 0 Higgs field, but it also corresponds to certain holomorphic bundles. And then what you do is you compute enough Betti numbers in each case to show that they couldn't have been homotopic. They're not even homotopic, let alone admitting a deformation retraction. Okay, that's basically what you do. You have to do this thing called deforming this moduli space is something called the nilpotent cone, and anyway, and then that gives you a means to do the relevant calculations. Okay, so let me go ahead and move on. And from this point, this is a pivot point. This is just to tell you about where the name comes from, at least a little bit. So in more general than just hyperbolic surface groups, if you look at the fundamental group of a Kähler manifold, then the character variety is homeomorphic to the moduli space of what's called G Higgs bundles with vanishing Chern classes. This is an example of the non-abelian Hodge correspondence. The K character variety is homeomorphic to the moduli space of flat holomorphic principal bundles. And what you can show is that this moduli space M is a partial compactification, not a full compactification. It's partial compactification of the cotangent bundle of the moduli space, which I denoted by N, the one that corresponds to holomorphic principal bundles. Now, the cotangent bundle deformation retracts to N, but it's a partial compactification of that. So that means you're generally adding boundary divisors in the partial compactification. And so you would expect, like adding a point to R2 to get, a sphere, you expect when you add boundary divisors, you expect the topology to change. So you would expect, that these moduli spaces all to have different topologies, generally, at least in the case of Kähler manifolds. And indeed, the previous theorem shows that in fact does happen, okay, in this example for these Kähler manifolds, namely hyperbolic surfaces. So if this doesn't happen, right, like a gamma has the property where this general philosophy doesn't happen, well, you might say that gamma has a deficit. And so that's sort of one reason why you might call it flawed. Okay, it has something wrong with it. Okay. The other reason we call it flawed is because, Florentino and Lawton, we invented it. Okay. So nilpotent groups, these are groups where the generalized abelian groups, and they're groups where you have something called the Laurel central series, which is defined inductively. Start off with gamma, then start looking at commutator subgroups. And a nilpotent group is one where the sequence of subgroups terminates, eventually becomes trivial. Okay, so abelian groups have this property, and nilpotent groups are more general. Okay, so Bergeron in 2015 showed that, in fact, that finally generated nilpotent groups are flawed and real flawed as well. So this generalized Carlos's and my theorem in the abelian case. And the proof was a really ingenious use of the ideas we used to prove that free groups were flawed, compounded with ideas that were used to prove abelian groups were flawed, the eigenvalue scaling idea. But there was a new idea. There was a number of new ideas, but one of the main new ideas was identifying the Kempf-Ness set as consisting of what we'll say as normal representations, normal homomorphisms. And these are ones where when you list it as a tuple of matrices, each element in that tuple is normal. And what does normal mean? It means that we should, it generally means that the elements commute with their Cartan involutes. So what's a Cartan involute? Well, you should think of the Cartan involution as just essentially conjugate transpose. And what you're saying is the matrix A commutes with conjugate transpose. I mean, in the case of unitary matrices or a unitary representation of the group, of the compact group. But anyway, but more generally use the Cartan involution. Okay, and you can show generally with respect to certain choices that the set of normal representations or normal homomorphisms always is inside the Kempnes set, but it's not generally equal to the Kempnes set. But for nilpotent groups, one of the key ideas in Bergeron's proof was to show that the Kempnes set is exactly the normal homomorphisms, or normal representations. Okay, so in our newest paper, Carlos and I do a number of things, but one of the main things we do is we generalize Bergeron's result to show that free products of nilpotent groups are flawed and real flawed. Okay, so we go a little further, and basically the proof is you will define a group gamma to be strongly flawed if the G homomorphisms K equivariantly deformation retracts to the K homomorphisms. Okay, and then we show in general that strongly flawed implies flawed. Okay, and then we also show free products of finally many strongly flawed groups are flawed. And then last but not least, we dig into Bergeron's proof and we say, oh, well, Bergeron actually proved that nilpotent groups were strongly flawed. That was actually in his paper. Okay, so we make that observation and then the result follows. And I guess we're out of time. So I'll just summarize here. The right-angled Lawton groups sort of interpolate between free groups and free abelian groups. It's a general class where you have some generators and some things commute and some things don't. One of our other results is we say that certain right-angled Lawton groups are flawed, and other ones we can't show fully that they're flawed, but we can say that there's a distinguished irreducible component. Irreducible in the Zariski topology. I'm mixing topologies here a little bit, but we can still talk about what that means. It's still, there is a Zariski topology, so a distinguished irreducible component in that topology, where the flawed condition actually holds for that component. That's the best we can do for now. We'll call that latter properly special flawed. I'm not going to the comments on proof. I'll leave this alone. We don't have time anymore. And then we also start dipping into the question of are groups that are flawed virtually flawed. So in other words, can we add in some kind of like finite piece to known flawed groups? So in that case, we say the simplest case of that idea would be, we know free groups are flawed, so let's put a finite group times a free group. And we know nilpotent groups are flawed. Let's look at a finite group times a nilpotent group. And in those cases, in one case with the free group, we can show that actually that such groups are flawed. And in the other case, we can't quite show it's flawed, although we think it is, but we can show it's still special flawed. So there's a component which has the flawed property, at least. Okay, and then the conjectures are that since we have a number of cases of rags that are special flawed or flawed, we actually conjecture all rags are flawed. But we don't have a proof. Let me just say one thing about that proof with the rags. What we can prove generally, though, is that the moduli space does deformation retract to the elliptic representations generally. But going from elliptic to unitary in general is the obstruction, and we don't know how to do that in general. But in some cases we can, some cases we can't. Okay. We can generalize the notion of a knot group to a generalized knot group, and we have reason from looking at examples by Vicente Munoz that to conjecture that generalized knot groups are flawed. He essentially worked out the topology for SU2 and SL2, and he didn't make the comparison, but if you do make the comparison, you see that they are homotopic to each other. So from that example, we're making this conjecture. We know that all closed hyperbolic surface groups are flawless, so we conjecture that all non-abelian Kähler groups are flawless. The abelian Kähler groups actually are flawed. That follows from our theorem about abelian groups, because abelian Kähler groups are just ones where the free part is even rank. Anyway, so that's just a special case. But for non-abelian ones, just like for closed hyperbolic surface groups, we think that those are going to all be flawless from the philosophy, the remark I made earlier. A classic group that generalizes nilpotent groups is super solvable groups, and we've thought about this a little bit and dug into the weeds a little bit about the structure of super solvable Lie groups. And although we don't have a proof, we do think we have enough evidence to actually conjecture that super solvable groups are flawed. But anyway, we'll just state as a question: are finally generated super solvable groups flawed? And then we also have that, we showed that free products of nilpotent groups are flawed. That was like the main theorem that I spent a little time with today. But you can generalize free products to graph products. So the question is, are graph products of finally generated nilpotent groups flawed? And then lastly, thinking more like a geometric group theorist, if two groups are commensurable and one is flawed, is the other flawed? That, I think, is a very provocative question. And I thought about it a little bit, and I don't have it. I thought I felt comfortable conjecturing it, but at this point, I'm not sure anymore. But I don't have a counterexample or a proof, so I'll just leave it as a question. And that, ladies and gentlemen, is the end of my talk. Sorry, went over. But these are the references. Some numerous, papers that I have mentioned today, and this is the newest one: free products, where we show free products and nilpotent groups are flawed, and some rags are flawed. Yeah, I'll go ahead and stop there. The Simons Foundation helped us to help fund my work. So, I'll just give them a plug. All right. So thanks so much. Are there any questions?